Well, it's a great pleasure for me to be back in Warwick, and you see more or less what my talk's about from these two slides here. And these pictures being, you have to think of this as space-time pictures where time is going up the picture, and that will be how my pictures normally go, and space is going sideways. So this describes a model which is finite. It's like a circle if it was only one dimension, but it's really a three-dimensional version of a circle, or of a sphere is, of course, two-dimensional version of a circle. And it reaches a maximum and then comes back down again. So this was an early model in accordance with Einstein's general theory of relativity. This was put forward, I think, in about, I forget the exact date, but in the early 20th century, 1917 or so. And Tolman introduced a model which he tried to incorporate the second law of thermodynamics. Of course, something has to progress and get bigger and bigger as time goes on. There are other models in which they're more wilder than these ones, where black holes somehow sprout new universes and things. I don't want to talk about those, but just I should talk about them, then you'll see that my own scheme is not that wild after all, because there's some a lot wilder. These other ones, for example, involve higher dimensional things called branes which collide and so on and so forth. I don't want to go into all that. That's a version of string theory and so on. No string theory in my talk, you'll be pleased to hear. This is more of a saying what the second law is telling you, that the entropy is a measure, and actually it's the logarithm of a number of possible ways of assembling the given macroscopic state, including all the motions, out of its submicroscopic ingredients. So you can absorb that if you like. Basically, it's a measure of randomness. And thermal equilibrium is where it's going to end up. That's what people used to call the heat death of the universe, when the entropy has reached its maximum. And so that's a pretty miserable kind of state to end up in. Now, here is what we believe now the universe is more like. It has this thing called a cosmological constant. People refer to that as dark energy. I prefer the term cosmological constant. That was one that was introduced by Einstein when he had the idea, I think in 1917. And now observations seem to indicate that it's present. And what you have in these, they're very slightly different models of the universe, depending on if it's open or closed or what, but they all basically follow this pattern. You have a Big Bang at the beginning, and there may be a thing called inflation, which takes place right early, tucked in the middle. You wouldn't see it in this picture. I personally don't believe in inflation, because the scheme I'm going to talk about does just as well as what this thing does, but don't worry about that. This is what the universe seems to be doing. We're somewhere up here, about there somewhere, where it started to accelerate in its expansion. And that is due to this thing called the cosmological constant, or what people refer to as dark energy. I don't like the term dark energy because energy, according to E equals mc squared, is equivalent to mass. And mass is thought of as something attractive, whereas this thing is repulsive. It pushes the universe apart. And so energy is not a very good picture of what it is. It's just this term in the equations. If you don't like it being a term in the equations, well, that's the best we can really do, I think. But what about the best evidence we have for the existence of the Big Bang? Why do we think it's there at all? Well, there are various reasons. There was an earlier model called the steady state model, in which there wasn't a Big Bang, but you needed to violate Einstein's theory and all sorts of things. And more seriously, you had to violate some observations. The most critical is this thing called the cosmic microwave background. Now, the cosmic microwave background is radiation coming in from all directions, and it was discovered sort of accidentally. But one of the most remarkable things about it is this in this graph here. I won't talk about that in detail, but here we have the different frequencies, or the different energies of photons, if you like, going lower and lower. The frequencies are going lower. The frequencies are going up and up and up. The energies of photons are going up and up too, this way. So this is the spectrum you see, and these are very good measurements. The error bars are these lines here. The theoretical curve is that. The error bars in this picture are magnified by a factor of about 500. So really, you have to squash these down, even the worst one, which is this one, down by a factor of 500. And you see the observations hug this curve to an extraordinary precision. Now, this is one of the things that got the Nobel Prize for the cosmic microwave background. In fact, it got it twice, two separate occasions. Very remarkable observation, telling us that there's the Big Bang. And it tells us not only that, but this rather paradoxical feature, because what is this curve indicative of? It's the famous Planck black body curve. It tells us what you're looking at is thermal equilibrium. What's thermal equilibrium? Well, I just said thermal equilibrium is a state of maximum entropy. When you go back and back in time, since the entropy is going up in the future, it must have been getting smaller in the past. So you shouldn't see a maximum, you ought to see a minimum. So that is a sort of paradox. Well, people had all sorts of ways of trying to explain the paradox, which I'm afraid most of them aren't right. The real explanation is that this does not take into account all the physics. What are you seeing in this microwave background? You're seeing photons and particles, charged particles, milling around randomly. It's random as far as the particles are concerned, but that's not the whole story, because it misses out one very important part of the story. The important part of the story is gravity. Now, to see what gravity does, if you imagine a gas in a box, now this is the second law in action. Suppose initially it was tucked in one corner. As the entropy increases, the gas gets more spread out uniformly over the box, and it looks sort of like this. So this is an increase in the entropy, and it's consistent with the sort of picture I was showing you before. You see, the point of this picture is that you can have dynamics like Newton's laws, for instance, which are completely reversible in time, and this is perfectly consistent with Newton's laws being in that direction. What you don't see is a smashed glass on the carpet with all the wine absorbed into the carpet suddenly collecting itself and jumping onto the table. That will be just as consistent with Newton's laws as this is, but you never see that. Well, we don't see that, and what we say is it disobeys the second law of thermodynamics, because the entropy is going up and up and up, and the second law tells us it shouldn't go the other way. Well, that's just a statement. It doesn't say why. Now, here you see the entropy is going up, in this case, but suppose these aren't molecules of gas in a box. Suppose these are stars in a huge box. Now, it shouldn't matter how big the box is. The second law should be acting just as well. But what you find is, because gravity is there, these things start to clump. And eventually they clump into a thing called a black hole. And this represents increase of entropy. So the entropy is increasing. This is increasing here. But the pictures look completely different. What we see in the Big Bang is a mixture of, let me put the universe back here, is a mixture of this and this. You see a combination of those two things. So as far as the matter is concerned, that's what you see in the cosmic microwave background. Yes, the entropy is very high. But that is not the whole story, because you're also seeing a uniform state. Because not only do we have this Planck spectrum, that was very imposing observation, but you also see uniformity over the whole sky. So it's another observational fact that it is uniform. And this is low entropy with regard to gravity. So this is a very curious, imbalanced situation. And just to bring it a little bit more into familiar things, the reason we're all here, happy and healthy and whatever we are, is because we are taking advantage of this clumping due to gravity. Why is that? Because it's the sun. You see, the sun is a source of, well, actually, you see, you think of it as a source of energy, but it's not really, because all the energy we get from the sun simply goes right back out into space again. Well, we keep a little bit of it in global warming, I'm afraid, but apart from that, which in this picture is a small effect. On a large scale, I'm afraid it's too big an effect. But we do see that the energy is more or less as much going out as comes in. So that's not the key thing. The key thing is the energy comes in the form of a lower entropy. That is, a smaller number of photons, because these are more energetic individually, the photons. A larger number of not so energetic photons go away at night. Infrared ones, yellow ones coming in, say, and these are individually more energetic. And so therefore there are fewer degrees of freedom in these photons than there are here. So this is a low entropy organized state. The the plants, the green plants, take advantage of this, and we take advantage of that by eating them or eating animals that eat them. And that's how we survive. Now, why is this sun a source of low entropy? Well, basically all sorts of things are going on, nuclear reactions and goodness knows what. But the key thing is it's there at all And it's there at all because of gravitational clumping. So it's just this effect I've been talking about. And as it clumps, it gets hotter. And okay, thermonuclear actions keep it going, but that's the key point is that it's held together by gravity, and that's the key point. Now you see, what's the maximum entropy situation here? It's a thing called a black hole. So let me try and say something about a black hole. I'm going to draw you a picture of a black hole. Well, that's not what you'd actually see if you saw one, but if you had a space-time description of a black hole, that's what you would have. Now the key thing about this diagram is not just that it's a space-time picture, time going up the picture as before, space going here. So here you have the black hole collapsing, and here we have this thing called the horizon. Now the horizon, the key to understand the horizon, what you need really to understand is the light cones. That's the key thing. The key thing in my talk are the light cones. That they're absolutely crucial. They are the structure in space-time, the most important structure in space-time, and they tell you how light would travel. You see, you have to think of a light ray, or at least a photon zipping along at the speed of light, in this space-time picture would be a curve, you see. And that curve is always tangential to the light cones. These light cones just tell you what the speed of light is at any point. And if you think of a spatial description, you take sections through this cone as time goes on. Bear in mind, time is one-dimensional going this way. Space is three-dimensional going this way. I can't draw that very well. I've had another go here, where you think of the sections through it, although they look like circles or something, they would really be representing spheres. And this light cone represents a flash at in the middle here, expanding outwards with the speed of light. And it represents the limit of what massive particles can do. So here we have a massive particle. It's not allowed to go to the speed of light. It has to have its world line, as this is called. That's the history of that particle within the light cone. Whereas light itself can travel along the light cone. Nothing is allowed to get outside the light cone, so you can go back to this picture here and see the light cones get tilted in because of the gravitational effects of this body here, and this means that there's a place where the light cones are all tangential to the time direction. You have to travel the speed of light to stay in the same place. It's a bit of a paradox, but that's what it's doing because the light cones are all tilted over like this. And even further inside, they're tilted even more, so nothing can escape without violating this condition I was giving you over here. Even worse is this thing in the middle, which is a singularity. That means that space-time gets horrendously curved up, and physics more or less has to give up. Here we have, well, it doesn't quite. Here we have general, this is sort of special relativity when the light cones are all organized uniformly and there's no gravity. When there's gravity, they're a bit all over the place. But the rules are the same. A massive particle has its world line within the light cones. A light ray or a light particle travels along the light cones. Now, I have to improve this picture a little bit now by putting in the black holes. We do know there are actually some absolutely enormous black holes. There are much bigger ones seen, some which are of the order of 10 to the power 10 solar masses, which I think that's the record you can see. So that's the sort of end point, what things do when they start collapsing. So we should put the black holes into this picture. And we have now singularity at the beginning, the Big Bang. That's where physics gave up. It didn't give up. It moved up and go backwards in time. It was the beginning of time, according to the standard view. And here we have these black holes going on. Well, I've also put something else in. This is more or less to scale. I put in some things called pop here. It's according to Stephen Hawking, and I believe him. It's on this the black holes actually, because of quantum effects, do have a temperature which isn't quite zero. It's very nearly zero. You have to think of the lowest temperature ever made on the Earth, and that's about the black holes actually, because of quantum effects, do have a temperature which isn't quite zero. It's very nearly zero. You have to think of the lowest temperature ever made on the Earth, and that's about as warm as they get. They get a lot colder than that too. The big ones are even colder. But eventually, when the universe expands and expands, this cosmological constant means it has this exponential expansion. It keeps on increasing its rate of expansion, and eventually it gets so cold but it's even colder than the black holes. And then they radiate away their mass and their energy and finally disappear with a pop. I'm calling it a pop, not a bang, because no matter how big that thing is to begin with, it's only a pop at the end. When I say a pop, it would be a nasty thing to go off in this room, I have to say. but it would be, from the cosmological point of view, it's a trivial explosion. Trivial, at least, from its magnitude. It has some implications, though. Okay, so that's the picture we have. And now why do we get these black holes here? Why aren't they there at the beginning, you see? Well, they could have been. No, if I haven't got my transparencies messed up, I should be able to show you. You see, what you can imagine is that the universe was collapsing. And let's not have the black holes, because they shouldn't be there. You start off with just matter, and normally it would not be completely regular. There would be irregularities. So there would be an expansion of the universe in reverse, but you would, you have a contraction of the universe, but you have irregularities, and these would cause clumping. And you would have black holes forming, and these black holes would, well, that's what people sometimes refer to as the big crunch. But the thing is, it's nothing like what you get at the beginning. We have a very nice, smooth beginning. That's our Big Bang. If it was a general mess of great, huge entropy, the sort of thing you'd expect when the black holes start to congeal, you'd have something which is completely unlike that. So now, here's the problem. Can we find an explanation of a sort for why it was special with regard to gravity and not with regard to anything else? But you see, I have to say something more about black holes, about light cones, not just what I said here, because we need to know something else. You see, the metric of general relativity is things that clocks measure, if you like. It's really a time. It tells you how clocks measure time. And this is something in addition to the light cones. And it's one more number. Where the light cones are is 9 numbers per point. One more tells you what the metric of geometry is. And this metric needs mass. That's the other thing to say. If you have this is combining two of the famous formulae of physics. E equals h nu, that's the Planck formula, and E equals mc squared, that's Einstein's formula. You put the two together, and that tells you that a particle has a kind of frequency which is proportional to its mass. This is basic quantum mechanics. And so any particle is basically a clock. If you take the particles away, if you just have massless particles like photons, there's no way of making a clock. Okay, so let's see what happens when we take away the, I think I'll never find this transparency in the negative amount of time that I have at the moment. Here we are. No, I found it. This one, that was my picture of space-time. But let me say that if you want the full geometry of Einstein, you need to put all these little things that clocks measure, which is the scaling. If you take that away, you have a slightly weaker kind of geometry, which is conformal geometry. Let's call it light cone geometry. Now, if you only know the light cone geometry, well, you see, why should I say only know the light cone geometry? Well, let's get back near the Big Bang again. Things get extremely hot near the Big Bang. They get so hot that the mass of particles becomes irrelevant. This is irrelevance to the LHC. You've probably heard about this great machine that's come back on again, which is supposed to have such huge energies that they're testing to see where mass is thought to come from, the Higgs particle and all that sort of thing. But once you get to higher energies than that, mass becomes irrelevant, or disappears in effect. So right down, tucked up near the Big Bang, particles don't have any mass, so they only know the light cone geometry. They don't know this geometry. And this enables you to do something more. What you can do is the following. You can do two tricks. One of them is a trick that my colleague Paul Todd has introduced in order to characterize the nature of the Big Bang. You can draw your picture again, stretching it out, so the Big Bang looks like an ordinary space-like region. So it's a moment where you have an ordinary stretched out space, you see. And the thing is, what you do, this is just a mathematical trick. You say, suppose that there was something behind this Big Bang, then that would restrict you to the kind of singularity we actually seem to have. It's a pure mathematical hypothesis. What about a remote future? You can do the opposite trick. You can squash infinity down, keep the light cones, and, although this is a longer story, I'm going to say all the black holes disappear by the Hawking thing, and you're left with nothing but particles which have no mass. That requires more discussion, but let's suppose that's right. Then again, they only know the light cone geometry. They don't know the metric. So this is the trick, and you say, as far as the massless things, which are relevant right down here and they're relevant up there, the universe had two boundaries, one in the past and one in the future, and you could speculate that it was a succession of what I call eons. This is the kind of cosmology I'm referring to here, called conformal cyclic cosmology, where the universe goes through these cycles of a sort. It never collapses, you see. It just forgets how big it is. It gets to the stage where there's no mass left, and it can't remember how big it is. And you have to do some mathematics to make that make more sense. But that's roughly the idea. It forgets how big it is, and it thinks it's another Big Bang. As far as the massless particle are concerned, they just carry right on through as though nothing had happened. Okay, that's the story. There are observational implications of this, which I could go into if anybody wants to ask me about it, but I think I've got negative time left, so I better stop. Thank you very much.